Welcome to the NASA Goddard Space Flight Center here in Greenbelt, Maryland, where we're building the flight and ground modems for the Laser Communication Relay demonstration. LCRD is a technology demonstration mission that will use infrared lasers to send and receive data at above a gigabit per second in a relay capacity. Multiple systems are being incorporated into LCRD to create this communications relay capability. In addition to having a flight payload, we'll also develop a ground system for the payload to talk to. On both sides, we'll have modems that act as modulators and demodulators for signals received through the optical modules. Today we're going to take a closer look at both our flight and ground modems and see how we've been developing those. Come on in. Hi Rick, how are you doing today?
Great. I'm excited to talk about these two modem subsystems we've been building.
Wonderful. Rick is the development lead for modems here on LCRD, and if you're ready, let's go take a look at the systems.
Absolutely.
So let's get some basics straight. What are the modems? What are their functions in the payload and the ground system?
So the basic function of a modem is to take information and transform it into another medium. So in our case, that means we take digital data and transition it into light and the reverse. So basically how the modems work is they receive digital data at the ground station. The ground modems transition that into light. It goes up through the ground station telescope onto the spacecraft payload, where it is received by the flight modem. The flight modem then takes the light that was received, transforms it into digital data for further processing by the payload.
I see. Now, correct me if I'm wrong, but you started out with the ground modems, right? Why is that?
Yeah, so if you can see the flight modem behind me here, it's a very compact system, but there's a lot going on in there. There's 17 circuit boards, several hundred splices, and so the first thing we did when we got the design was we wanted to learn how it operated. And so we transitioned this design into a rack-based design like you can see behind it. Mm-hmm. That gave us a lot more room to work, and we were able to use that room when we were troubleshooting things, learning how to test it, writing our test procedures, that sort of thing.
I see. Can we go check out the codec?
Absolutely.
Awesome, let's go. So I've heard that you need the codec to be able to get through the atmosphere. What is the codec and what does it have to do with the modems?
So one of the things that you're dealing with in optical signals is severe atmospheric effects. Things like wind, rain, and certainly clouds can severely degrade optical signals. And so we developed a system called the codec that would apply forward error correcting algorithm to the data and time-spatial interleaving. What this does is it allows the data, even if it's corrupted, to be reconstituted on the other end of the link.
Okay, all right. So then how do data rates play into the ground modems?
Well, one of the other knobs we have to turn is that we can slow down the data. This has the effect of increasing our signal-to-noise ratio, which means that we have a better chance of getting the signals through.
I see, okay. So I noticed that you guys have got the flight modems going on. How's development going with those?
It's actually going very well. We built up the first flight modem completely. It's in requirements testing right now on our bench. Soon it's going to go over to the environmental test facility that we have here at Goddard to complete its requirements testing. Our second flight modem is also under development. We've built up, we call them Tower A and Tower B, so we built up Tower A and we're in the process of building up Tower B. We expect that work to be complete in 4 to 6 weeks, and then it'll follow the same flow as the first flight modem.
That's great. So then how does developing modems for flight differ from developing modems for the ground?
So flight modems, flight systems in general, need to be able to survive two things. That's the launch environment and the operational environment. And so what we do at Goddard is we take our systems that we design over to the environmental test facility, and we do things like vibration, which ensures that we're going to survive the launch environment. We also perform a test called EMI-EMC, which ensures that the modems are not susceptible to or do not interfere with other systems on the spacecraft. And finally, the big test is thermal vacuum. And that's where we operate the modem over its operational temperature range in vacuum to ensure that it meets its performance requirements.
Oh, that's really cool. So then what does the space switching unit have to do with the modems?
The space switching unit is actually the heart of the LCRD payload. Not only does it provide command and telemetry interface to the modem, it also processes our digital data and transmits data between our two flight modems.
That's great. Can we go check out the electro-optic components?
Absolutely.
Awesome, let's go. So is there anything special for LCRD that you'll have to do for the modems?
Actually, typically when you're designing a flight subsystem, you start out with a set of well-vetted electronic parts that are designed for spaceflight use. In our case, since optical comm is so new, the electro-optic components are not really designed for space. And so what we have to do is we have to buy them from commercial houses and perform the upscreening ourselves to ensure that they will survive while in space.
This has been really great, Rick. Thanks so much for letting us come in here and visit today.
Anytime.
Want to learn more about LCRD? Visit lcrd.gsfc.nasa.gov.